My name is Suho Shin, and I'll present Delegating to Multiple Agents, which is joint work with Hajiaghayi and Keivan Rezaei. So consider a decision maker, say principal, who wants to solve a task. The principal, however, does not have expertise nor time to solve the task by herself, so she instead delegates the role of solving the task to some experts, which we will call as agents. Typically, the agents observe the solutions privately, while the principal can only observe the agent signals after the solutions are realized. If two parties have misaligned utility so that the agents have ulterior motives in the decision-making process, then a moral hazard may arise and the principal might suffer a low utility. For example, consider a university bears a cost of hiring a faculty member for computer science department, but delegates the role of hiring procedure to the department. University may want to hire someone who works on artificial intelligence, such as deep learning, but the department may want to hire who works on theoretical computer science or theoretical aspects of machine learning. And another very good example is a research granting procedure. Suppose that a research grant agency, such as government institution, wants to advance a specific line of research. This is usually done by funding individual or a group of researchers. Unfortunately, however, the agency may want to develop a fundamental technology which significantly affects the real world, but researchers might be only interested in publishing more and more papers in top conferences. To incentivize such agents to behave more in favor of the principal, a typical approach is to give some monetary incentives based on the outcome of the decision-making procedure. This is a very well-studied problem in the literature of contract theory. However, often in the real-world scenarios, monetary transfers are not allowed between the principal and the agents. Or one can interpret that the reward for the participation is determined exogenously from the mechanism so that the principal cannot commit to additional monetary incentive. In this case, the agent's utility is solely based on the solution finally selected by the decision-making procedure. So our question is, what can be done for the principal in this case? One available approach is to commit to a predetermined eligible set of acceptable solutions. For example, suppose that the principal knows the distribution from which the agent solutions are drawn. And then what the principal can do is to smartly design a so-called eligible set, which only accepts the proposed solution if it belongs to the pre-committed eligible set. So given the eligible set, agent will observe the solutions and then best respond with respect to the committed eligible set. And then finally, the principal accepts or rejects the solution with respect to the eligible set. And basically, one can see that the principal fundamentally faces a trade-off between making eligible set restrictive or inclusive. For instance, suppose that the principal has alphabetical preferences over alphabet, but the researcher has anti-alphabetical one. If the principal designs the eligible set to accept only the high solution A, then with high probability, then the agent may not have such a solution. Then the outcome of the delegation mechanism will be just a null, and both of them are unhappy so that they realize the utility of 0. On the other hand, if the principal commits to accept solutions A, B, and C, then based on what the researcher has observed, the agent's best response will be to propose solution C. And then it is a little bit better for the principal in terms compared to the previous case, but this is still far from being optimal in hindsight, which is to pick the solution B. To summarize, the principal should smartly use the prior information regarding the feasible alternatives and design efficient eligible set. More precisely, suppose that the principal knows the distribution from which the agent solutions are drawn, and then this can be actually abstracted as having a probability distribution of principal's utility and its agent's utility for each solution. Then our objective is to construct efficient eligible set to maximize ex ante utility for the principal. And in this kind of problem, surprisingly, Kleinberg in EC 2018 proved that a very simple threshold-based eligible set achieves half approximation to the optimal solution in hindsight. And actually, the proof is based on a very novel connection to the well-studied proof of inequality from the economics and computer science. And in this context, our paper asks what will be the additional gain of the principal from having multiple agents to delegate. For example, let's consider a very simple example. So if there is only a researcher one as in the figure, then without any eligible set, it is very obvious that the agent will propose solution D, which is the best for the researcher one. However, suppose that there is another agent with solutions C, D, E. Then, since agent one solution D probably will be dominated by solution C by agent two, since the principal will select the solutions obviously in the alphabetical order, agent one may think that he should submit solution B, which dominates all of the agent two solution in terms of the principal grant agency's utility. So as in the example, having multiple agents seem to intuitively make things better for the principal, since it constitutes a competitive tension between agents. However, it is not still clear to what extent it helps the principal. For example, can you obtain constant approximation or even without the prior information about the agent solutions? Or under what regimes would it help the principal significantly? For example, does it still help the principal if the agents do not have complete information regarding each other's solutions? Or what happens if the agents are very symmetric in terms of the obtainable solutions qualities? Our paper mainly answers all of these questions by conducting a comprehensive study on a multi-agent delegation problem. And now we will start presenting the formal problem setup. So there is a probability space of solutions, including a null outcome. And each agent I draws a IID samples from a given distribution for each I that belongs to N. And for each solution, there is a random mapping from the sample solution to the utility for the principal and for the agents. Note that the utility function for each agent may be can be different from each other. Given the principal's utility x of omega, we compare our mechanism's efficiency against the first best solution in terms of the principal's utility, which is when there exists no moral hazard of the agent and all the agents just truthfully propose solution that maximizes the principal's utility. So it's very important to model the information structure between the players. So for the agents' information regarding each other, we consider both complete information under which each agent knows all the other agent solutions, and also we study incomplete information setting under which they only know the prior distribution of the other's agents. For the principal's information, we first study Bayesian mechanism in which the principal knows the distribution of the random utility of the solutions by the agents. And then we also study the prior independent mechanism where the principal has no information regarding the distribution at all. But due to the time constraints of the presentation, we will only present on the prior independent mechanism for this presentation. To give an overall description on how our game proceeds, the principal first commits to a mechanism which possibly is equipped with an eligible set, and then each agent draws random samples from it, and then each agent sends signals privately from each other to the principal, for example, like a subset of solutions or some statistics of them, and then the principal chooses final outcome with respect to the committed mechanism. And if a solution is selected, then the principal and the selected agent who owns the solution realize positive utility, whereas all the other players' utility will be 0. And if the selected outcome is just a null, which means that there is a no selected outcome, then all the players realizes utility of 0. We focus on a very restricted class of mechanism, which we will denote by multi-agent single-purpose mechanism, or MSPM. So basically in MSPM, the principal first announces an eligible set for each agent. And it further requires each agent to propose only a single solution. And then it finally chooses the final outcome based on the pre-specified rule, which determines the final outcome based on what agents have proposed. And interestingly, we show that it suffices to consider the class of MSPM, and the proof is via revelation principle style of argument. And correspondingly, we prove that if the agents are symmetric, then there exists constant approximate prior-independent mechanism. And further, if the cumulative distribution function of the utility random variable satisfies monotone hazard rate, then we prove that there exists asymptotically optimal prior-independent mechanism, where asymptotical means that in terms of the number of the solution per agent and number of the agents. To prove this, we consider a simple prior-independent MSPM, which does not announce any eligible set at all. And the selection rule is to simply select the best solution in terms of the principal's utility. Then we show that such a mechanism's performance is lower bounded by first best solution of the second best agent for any Nash equilibrium in terms of the principal's utility. And then we quantify such a lower bound by providing several new technical results on the expected spacing between order statistics. And then the result follows. If the agent does not completely know about each other's solution, then it significantly complicates the equilibrium analysis. So actually, this is denoted by Bayesian game in the literature. Because each agent computes the expected payoff regarding with respect to every possible realization of the others players. So typically in Bayesian game, it is hard to quantify the payoff of even a certain action of a single agent, since it needs to compute every possible realization of the other agents types. And further in our problem, since each agent is characterized by multiple random variables, not a single random variables, because each agent is equipped with multiple random solutions, it becomes even more complicated. For example, like even for two agents, computing one agent's payoff entails analyzing the realization of multiple random solutions of the other agents, and it largely complicates the analysis. So in order to tackle this challenge, we obtain our main results using a mild notion of solution concept of approximate base Nash equilibrium. And our main results in the Bayesian setting, in the incomplete information setting, is such that if the agents are symmetric and all the agents are equipped with uniform distribution, and further, if the utility between the utility function of the principal and the agents are independent from each other, then there exists a prior independent mechanism with constant approximate base Nash equilibrium, such that for this approximate base Nash equilibrium, the principal obtains optimal utility. So the proof is largely based on the correlation inequalities called as FKG inequality to wipe out correlation between the ordering of the agents and the ordering of the solution within the agents for the approximate Nash equilibrium to analyze the approximation factor of the certain events, and also the proof is based on analysis of joint distribution of order statistics. And using a very similar technique, we show that there exists exact base correlated equilibrium with constant approximation ratio, where we do not present the much more details in what the base correlated equilibrium is. And finally, although the conditions in the above two theorems here look very restrictive at first glance, because it requires the agents to be symmetric and all the solutions to be sampled from uniform distribution, and all the utilities are independent from each other. But we show somehow that these conditions are necessary to have those kinds of positive solutions. So that without symmetric agents and independent utility assumption, there exists a problem instance such that any mechanism admits base Nash equilibrium with arbitrarily bad principles utility, which means that principles utility can be almost close to zero. To summarize our paper, we basically conduct a comprehensive study on Bayesian and prior independent mechanism for the multi-agent delegation problem. And the main takeaway is that the competitive tension that arise because of having multiple agents here helps a lot in terms of the principles utility. But it largely depends on the information available to the agents and the correlation between the agents and the principles utility. For example, in the complete information setting, it was like the principle can obviously achieve some better utility, but in the incomplete information setting, we actually require that the principles and agents utility needs to be independent from each other, and the agents need to be symmetric in order to making them very competitive. And to briefly summarize on possible future directions, it might be interesting to analyze exact base Nash equilibrium in the Bayesian setting, or it might be interesting to endogenizing agents cost to search for the solutions in the multi-agent setting. So actually in the single agents paper by Kleinberg in 2018, they also introduced a model under which the agent is equipped with a solution, a potential solution, but agent faces cost to actually observe that solution. And they somehow connect this problem setup to the classical Pandora's box problem and drive several results. And it will be very interesting to see how this kind of problem setup will extend to the multi-agent delegation problem. Thanks for listening to the presentation. And this is the end of the presentation.